Hello, this is a video where I'm going to run through two Jupyter notebooks, and it's sort of part two of a video that I made a couple of weeks ago on volume scattering in snow. This video is going to cover surface scattering and also how we can combine a surface scattering with a volume scattering model and make a slab total scattering model. So all of the interactive plots that I'm going to show are available online. If you just go onto the GitHub page, there should be a link in the description of this YouTube video, but you can also just find it with some Googling. And you can launch Binder. So just click on one of these buttons. The lower three choose an individual notebook, and the top one will take you to a menu of the notebooks. And that will spin up an instance of a virtual computer in the cloud from which you can just run through the notebooks like they're on your home computer. It takes a couple of minutes because it's downloading lots of modules like SciPy that aren't that small. So in the meantime, I'm going to start on some notebooks that are on my local machine and then switch over later. So let's start off with surface scattering. The most simple way that you can model surface scattering is just a reflecting wave from a completely smooth surface. And the amount of energy that's transmitted and the amount of energy that's reflected in that situation are governed by these things called the Fresnel coefficients. So we can look at the Fresnel coefficients as a function of the incidence angle here. And the first thing you can see from this plot is that it matters whether you're in the vertical polarization or the horizontal polarization, and the refractive index of the medium that you're entering does matter. In fact, the refractive index of the medium that you're going from also matters, but in this graph I've just assumed you're going from air into something else. So feel free to have a little play with the refractive index slider. One thing to notice is that the place where I've marked in this graph with a little green vertical line, that's Brewster's angle, and that's where the vertically polarized wave is completely transmitted into the material of interest. And that always exists independent of refractive index for some angle. And it's important because as we move to more complex surface scattering models, the V polarization is often less backscattered than the H polarization. And that's because even if you're not at Brewster's angle, the fact that there is a range of angles where the V polarization is completely transmitted through the interface, that is important in terms of how much is reflected back at your radar detector. Another way that we can visualize these Fresnel coefficients is by looking at a sort of example ray, like in a ray diagram. So you can play around with this here and see how obviously the angle of transmission changes, but we're not super interested in that. We're mostly interested in the amount of energy that's reflected. So I think if I switch to V polarization, I'm probably going to get less reflected now. In fact, almost nothing. So 60 degrees is pretty close to the Brewster's angle for a material of a refractive index of 2. But if I change it away, we will get a small little arrow, a green arrow appearing. There it is. So that's good fun to play with as well. But now we're going to move on from this smooth interface assumption and use a model called the improved integral equation model. And that models bistatic scattering from a rough surface. And by bistatic I mean you could situate an emitter and a detector in different places, so you can look at the distribution of angles over which a wave is reflected. So for these smooth surfaces, we're just saying that the angle of incidence is the angle of reflection, but in reality a rough surface is going to reflect a wave over a range of angles, and modelling that is really the big challenge in surface scattering models. So this is plot number 1. The incident wave is represented with the green arrow, and you can see the blue and the red lines represent the angular distribution of backscattered power. So you can see, because of that thing with Brewster's angle, the HH is a little bit more powerful than the VV, and there's a distribution of angles over which the power is reflected over, and that distribution of angles is going to increase as we increase the roughness. So sigma h here means that's the standard deviation of the height of some surface that we're modelling, and as we increase that, we're going to see that angular distribution broaden out into a sort of almost a sort of semicircle there. The role of frequency is also really important. So we're really interested in what the radar wave sees as the roughness. So that's sensitive to the wavelength itself. So at higher frequencies, a given roughness physically has a higher electromagnetic roughness. So it's easier to show than to say. As we increase the frequency, again we see a broadening of that scattered distribution of power. And as we drop the frequency, we're going to see a more specular distribution of scattered energy. This is a little slow, this graph, because of there's some really nasty like double integration going on under the hood. So in this plot we compare polarizations, and we can set the frequency with this slider. But what might be more interesting for our application at CPOM is to plot the Ku and the Ka frequencies. And we're particularly interested in the backscatter direction. So we're not massively interested in, if you ping a wave in at 40 degrees, what does it look like at minus 40? We're really interested in how much energy returns to the detector. So that's what's plotted on the right. I really, again, encourage you to spin up this binder environment by clicking the button on the GitHub and having a play with it yourself. I'm just going to demonstrate some stuff about what's going on here. I've got to stress that the correlation length here, that's the correlation length of height anomalies on the surface. So that has nothing to do with the microstructural configuration of the snow. So once again, we can see that if we increase the roughness, we get a more isotropic scattering. And if we increase the refractive index, we also increase the amount of scattering. Because there's just a higher dielectric boundary, which is what basically causes reflections. And if we lengthen the correlation length, we can see that the reflection actually becomes more specular. And a longer correlation length basically equates to a smoother surface. So I'm going to drop the correlation length and it's going to become less specular. So there you go, have a play. Now I'm going to move on to a different Jupyter notebook. Hopefully I'm going to run this one in the binder environment, which is loaded, fingers crossed, still loading. That's a bit of a shame. I'm just going to jump straight into the one on my local machine. So the Ulabi and Long 2014 book comes with MATLAB code for a model called the SSRTR, which is the single scattering radiative transfer model with Rayleigh volume scattering. So I've translated that into Python, and I've made some modifications because it initially included a surface scattering model for soil that obviously we don't want. We want the improved integral equation model, and I'm feeding it with the improved Born approximation for the volume scattering rather than the Ulabi code, which models the snow volume as an independent assemblage of my scattering spheres, which is okay, but it's not quite state of the art, you might argue. So let's have a look and see what happens. The good thing about this model is that it's very simple. It's got two surfaces that produce backscatter, and it's also got a volume that's like the middle of the sandwich with the bread as the surface scattering. But it can also handle things like a photon going in and bouncing off the ice surface and then undergoing volume scattering from the snow and returning to the detector. So these are these 5 categories you can see in the legend of the left-hand plot. Blue is the just scattering, single scattering from the ice surface. Purple is single scattering from the snow surface. Orange is snow volume scattering, just straight back to the detector. And the green and the red ones are firstly the bistatic reflection, so it either bounces off the ice and then comes back from a volume scatter in the snow, or it does it the other way around. It volume scatters from the snow to the ice and reflects back. But there's only one scattering and there's only one reflection. That's the important thing. And the red is 2 reflections. So you can imagine it going into the snowpack, bouncing off the ice surface, and then coming up into the snow, doing a volume backscatter back down to the ice surface, reflecting back, and returning to the detector. But the red and particularly the green blocks are quite small, as you can see on the left. So we're really mostly interested in the ice surface scattering, the snow surface scattering, and the just the direct snow volume scattering. So how are all these affected by the geophysical parameters, some of which were measured on Mosaic and some of which weren't? One thing I have done for this graph that is important to note is that I've just set the surface height correlation length to a fixed value, because it's quite confusing if you're modifying the snow microstructural correlation length and also the surface height correlation length for the ice and for the snow. So I've just set that to a single value, but it's important to remember that is also important, and I could have put 2 extra sliders in for the ice and the snow surface height correlation lengths respectively, which are pertinent to the roughness. So what happens, let's start out by increasing the microstructural correlation length of the snow and see what happens. So immediately on the right you see we get more backscatter, so the black lines go up, and on the left you can see that the orange makes much more of a contribution to the total backscatter, so that we're seeing much more snow volume scattering there from the correlation length. Let's turn that back down to a value that we sort of saw on average on Mosaic, which is 0.2, 0.1 even. We'll turn the snow depth up now and see what happens. So once again, particularly on the right, on the KA, we see more volume backscatter from the snow. But that actually doesn't change the total backscatter very much. So we're exchanging the scattering mechanism there between the snow and the ice surface. We're not just increasing the snow and also increasing the total backscatter. So next I'm going to turn up the density of the snow. Intuitively I thought that this would actually increase the snow volume scattering, but the biggest effect here is increasing the purple block, and the purple block represents snow surface scattering. And that does make sense when you think about it, because we're turning up the dielectric contrast between the air and the snow. So the snow density in this model is affecting the snow surface, and it's not affecting the snow volume scattering, because that's affected by the microstructural correlation length. Just playing with the snow surface roughness now. That's the RMS height of the snow surface. That intuitively just increases the snow surface scattering. That's going to be the same with the RMS height of the ice surface. That's going to increase the fraction of the ice surface scattering. Temperature doesn't play a big role, so we can mess around with the temperature quite a lot, and it doesn't really do anything. There's a big caveat on that. It doesn't really do anything because it only has a small effect on the dielectric constant of ice in this model, and that's a weak effect. But of course, in reality, the temperature controls the liquid volume content of the snow, which leads me to point out that this is a model for dry snow that I've set up here. So in reality, if you took the temperature up, particularly if there's any sort of tool in the snow to -1, you're going to get a lot of liquid in the snow. You're going to get higher impedances, higher dielectric constants, and that's not effectively modelled in this in this setup. And finally, the behaviour of incidence angle is quite important, and this is sort of stated a couple of times in the literature what happens here, but it's not actually really backed up or properly cited, I think. So as we increase the incidence angle, we increase the contribution of volume scattering relative to the total, but we drop the total backscatter. So increasing the incidence angle, really what we're doing there is we're decreasing the backscatter from the ice surface. And that's because if the ice is not like completely rough, we're gonna be increasing the angle of incidence. So we're going to be broadly increasing the angle of reflection, although I appreciate that's over a distribution of angles. And we're going to be seeing less return to the detector. But if we increase that incidence angle at a higher ice roughness value, then that's going to have less of an effect, because there you go, see? So I turned up the ice roughness, and then I increased the incidence angle by the same amount, and the backscatter dropped by less, and the ice surface backscattering contribution dropped by less. And that's because there are still quite a lot of surfaces on the ice that are normal to the incident radar wave. So that interplay of incidence angle with ice surface roughness, and also in fact snow surface roughness, is really important, and it's going to be difficult to capture that behaviour in terms of our Mosaic project. But the take home on all of this really is that there are 7 sliders on this interactive plot, and there could potentially be 9 if I included the correlation length of the surface height variation. And with the exception of temperature, the model responds quite strongly to all of these, and it doesn't just respond linearly, so it responds to the movement of a slider based on the position of many of the other sliders, which is why the interactive plot is so good, but also poses a sort of problem for our ability to intuit what's going on there. I think I put correlation length at the top. There's microstructural snow correlation length, and that's because that is really a big deal, particularly at Ka. So the difference between 0.4 of a millimeter, if you look at the Ka snow volume scattering versus 0.1 of a millimeter, is absolutely massive. So that says a lot about the role of snow as a potential blocker for Ka and Ku respectively, but it also introduces the issue that this is a single layer snow model, and of course snow is stratified, it has stratigraphy, it has layers, and layers with different microstructural correlation lengths are going to behave differently. So even a small layer of very large grains, very large clusters of grains, is going to be highly scattering to Ka, and there's going to be a lot of snow volume scattering in that, but we just can't model it with this simple slab model that allows us to break down the backscattering contributions. Instead, we have to use a more complicated model like SMRT, but SMRT doesn't allow this simple breakdown of like snow surface, ice surface, snow volume, but it also doesn't currently have rough interfaces implemented, so we don't actually see the backscatter from the snow surface at all. Instead, it's like this primitive Fresnel setup where you only really get backscatter that features the snow volume, and perhaps it bounces off, it scatters from the snow volume and then reflects off the ice surface and comes back, and that sort of thing. So that's really limiting our ability to model copolarized backscatter with SMRT. Just quickly, if I go through these, the legend line by line. So in SMRT, we don't have the purple or the blue contributions to backscatter. We only have orange, green, and red. We only have scattering that involves the snow volume itself, and you can tack some reflections on either side of that scattering event. So it is possible to implement the improved integral equation surface scattering model into SMRT, and that's maybe something I'll do in the future, but I think it will be a pretty tricky job and may not be super rewarding in terms of time spent to output, but who knows, that's possibly something for the future.